Okay, it's my honor to be here. So the topic of the talk is practical cryptanalysis of JSON Web Token and Gawar counter mode implementations. So I'm a secure engineer. So basically, my job is conduct security reviews. What it means is to play the attacker roles in your academic papers. So we're talking about two topics. The first one is JSON web signatures security review. And I will show you how tricky and complicated design can lead to unsafe implementation. The second topic is kind of a low-level primitive, Gawar counter mode. It's widely used. It's used almost everywhere. But then its implementation are rarely checked. And then I will show you two other type of bugs that may leak authentication key. So basically, there is no 0 day today. All the bugs were reported upstream and have been fixed a year ago, or some of the bugs were recently fixed. So before we start, the most important lesson that I've learned over the years is the encryption input is mostly under our control, while the decryption of signature verification input is always under attacker control. And then we will use this observation over and over again to show how to exploit crypto bugs. So JSON Web Token is basically just a JSON token, but it provides signatures or maybe multiple signatures. It has ECDH, CBC HMAC encryptions. It has different formats. The format I will focus on today is very simple. It has a header, a payload, and signatures. And then, in particular, I will talk about Square Go Jose implementation, which is widely used by Google, Let's Encrypt, and Square Inc. Okay, so when I started, I have no idea what JSON Web Token is. So I just read the RFC, and this line really triggered me, because it says that in the signature, you embed the public key correspond to the signatures. So basically what it means that the attacker can generate a private public key pair and then send the public key together with the signature, with the hope that the receiver will extract the public key out and use that for signature verification. This is the design level mistake by RFC, and let's see how it leads to unsafe implementation. So Go Jose enable that feature by default. So any signatures have the public key embedded in it by default. So just for fun, instead of trying the public key, I try to send the HMAC key, and it also accepted. I don't even know what it means when you have a HMAC key together with the HMAC. So the next problem is I look at ECDH implementation in Go Jose. And then, like the first step is to check well-known attack, invalid curve attack. And then for elliptic curve, on this curve, you have to check whether the public key is on your curve. Otherwise, the attacker can send you a public key on a different curve with a small order, and then it can use Chinese remainder theorem to extract the private key. And then Go Jose doesn't have any check. One of the reasons is Go implementation doesn't have ECDH. So the developer has to do it themselves, and you can guess that they miss this critical check. Go Jose also have CBC HMAC. The HMAC is computed over the AAD, nonce, and ciphertext. And the last, pay attention to the last component. The last component actually makes the boundary between AAD and nonce unambiguous. And then I found a few integer overflow, but then I want to exploit it. I don't know how to turn integer overflow in Go into remote code execution, but how about HMAC bypass? So the idea is you want to shift the boundary between AAD and nonce. So assuming an attacker observes some 16-byte AAD, some nonce, and then some large ciphertext, what attacker can do is it will create a new set of AAD where if you pay attention, because of AAD size is too big, when you multiply by 8, it will be 64 because of integer overflow. So basically, the main idea is the attacker already create a new set of AAD, new nonce, new ciphertext, and then the HMAC is the same. So basically, causing HMAC authentication bypass. The last topic in Go Jose is support multiple signatures I rarely seen a real practical use case that actually use multiple signatures, but then it's in our RFC, so the developer has to develop it. So if you look at the signature verification, it checks whether one of the signatures is invalid, then the method just returns the payload. And what's wrong with that? The problem is the signatures not only covers the payload, but also the protected header, integrity of the header. So what the attacker can do is assuming that observe a valid signatures and a valid header and valid payload, what it does is it creates a new invalid header and invalid signature, and then it will send them together with the valid one. Now the victim called a verify method, it checks whether one of the signatures is valid, while the second signature is valid because it's what the attacker observed on the wire. So the victim will wrongly assume that the first header is valid, which may contain the revocation key. Okay, so let's move on to Gawa counter mode. This is kind of a primitive, low primitive. That I also do a security review for. So Gawa counter mode is kind of fragile. There are a few attacks in academic, but like when I first look at it, it seems that like people rarely look at its implementation. So for a recap, the Gawa counter mode has an encryption key and authentication key. The encryption is basically just counter mode, but the counter is actually increase every time modulo 2 to the 32. This is important, and then we'll come back to it later. The authentication tag is basically, if you look at the last equation, forget everything, it's just a polynomial of authentication key where the coefficient is the ciphertext. Okay. So basically, I look at one of the OpenSSL wrapper because we now don't want people to use OpenSSL directly. So we write OpenSSL wrapper, someone wrote it. You know, the safe OpenSSL allows you to configure what is the expected length of the authentication tag. So the safe one is you say, hey, I want only 16 byte of authentication tag, or maybe 12 byte, depends on the applications. But what the wrapper does is it gets the authentication tag that it receives on the wire and uses to configure the expected length of the authentication tag. So what it means is the attacker just send 1 byte authentication tag, then the wrapper will happily accept it. You may wonder why doesn't attacker just send 0 byte? Well, basically, OpenSSL just prevents 0 byte authentication tag. So 1 byte works nicely. Another problem is, as I said before, the counter mode actually works in modulo 2 to the 32. So if after 2 to the 32 blocks, the counter will be wrapped around causing counter collisions. And in counter mode, if you have counter collision and you leak plain text, and in GCM, if you have counter collision, you also leak the authentication key. So this issue is different from the IVRU issue because it happens even if users use a different IVs. And then I make a check for OpenSSL conscript, and then bouncy castle and OpenJDKA miss this critical check. And then it's especially dangerous in Java Cipher because it uses streaming API, meaning you can encrypt last file by calling encrypt each chunk. Okay, the last bug I will talk about is the classic timing vulnerability in OpenJDK. So if you look at this, it looks similar to the hashmark vulnerability. Basically, it compares byte by byte, and if it see the first unmatched, then it will throw an exception. Okay? So, okay, basically it allows you to bypass authentication once for particular ciphertext, but I want more. I want authentication key. So let's remind us about Anton Zhu forbidden IV attack. This works on encryption input under user control only, and then it's not exploitable in practice. And basically, this already fixes in 2007. But I remind us that decryption input is under attacker control. So let's see how it can be exploited. So the attacker chooses collided IVs in decryption. Basically, the attacker sends 2 pairs. The first pair is IV in C1, the second pair is IV in C2, and then C1 XOR C2 is 1. In particular, you just choose a very simple, simple payload, IVE 0, C1 is 0, and C2 is 1. And using the timing attack, the attacker can learn the authentication tag of these pair. So I write that equation for you. So basically what it means is if you XOR the authentication tag together, then you have H square. And then finding a square root in whatever field is enough to find H. So basically what it means is if you just make a small mistake similar to H mark 1, then you basically leak the authentication key. I have an extra bug, but probably it's better for questions. Thanks for your attention.
Okay, any questions for Quan? I guess not. Well, I guess you're going to be around, so if you want to talk to him in the coffee break, you can do. Let's thank Quan one more time. Thank you.